Hi guys, welcome back to a new IMONST video. So in this video we'll be talking about the senior only section for last year's questions, and these are problem 16, 17 and 18. Now for problem 16, because these questions are typically harder than the ones in the front, so this might take a lot more time, maybe 20 minutes, I'm not sure. Now let's look at problem 16. Find the number of positive integer solutions a, b, c, d to the equations a squared plus b squared times c squared minus d squared equals to 2020. And as you can see here, they have very kindly given out one of these solutions. So one of the first things we have to do is to break down 2020 into smaller parts. So what we can do is just break them down into pairs because we have two terms over here. So we can break them down into 1 times 2020, 2 times 1010, 4 times 505, 5 times 404, 10 times 202, and finally 20 times 101. These are the only 6 pairs. Now, let's kind of explore a bit of the characteristics of any pair of like a squared plus b squared and c squared minus d squared. As I've said somewhere before in the past videos, any n squared, so any integer squared, will be congruent to either 0 or 1 mod 4. So 0 meaning that this number itself is a multiple of 4, so this is for even n squared. And then 1 means that it is a multiple of 4 plus 1. This is for all at odd n, okay? So what we can do is for a squared plus b squared, the possibilities will be somewhere like, okay, 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1, mod 4. Now use 2 dots to represent the same thing. Will be equal to 0 or 1 or 2 mod 4, right? Then for c squared minus d squared, we would have something congruent to 1 minus 1, 0 minus 0, 1 minus 0, and 0 minus 1 mod 4. And then finally it will become 0 or 1 or minus 1, which we can add 4 to it, will become 3 mod 4. Now, notice that in a squared plus b squared, the a squared plus b squared is congruent to 3 mod 4 is absent. And then for c squared minus d squared, the c squared minus d squared is congruent to 2 mod 4 is absent, okay? So we cannot have both being, we cannot have both of these terms being congruent to 3 mod 4 or 2 mod 4. But as we can see here, in 2 of these 6 pairs, so 2 times 1010, so both 2 and 1010 are both congruent to 2 mod 4, so cancel. And then 10 and 202 are both congruent to 2 mod 4 again, so cancel. Now, what we have left is 1 times 2020, 4 times 505, 5 times 404, and 20 times 101. Now, let's kind of analyze and see if 1 times 2020 and 4 times 505 are actually possible to make any kind of like a squared plus b squared or c squared minus d squared. Now, let's just take 1 alone. So if we have 1 equals to a squared plus b squared, the only integer solution would be 0 squared plus 1 squared, or the inverse. But since 0 is not a possible number, 0 is not a positive integer, so this is not possible. Now, for 1 being the difference of 2 squares, it is not possible because the smallest one is 0, and then the next one will be 3, being 2 squared minus 1 squared. So 1 times 2020, the whole set is just eliminated. Now, for 4 times 505, of course, now let's just look at 4 itself. So can 4 be a sum of any a squared plus b squared? Well, possibly, but it's only 2 squared plus 0 squared. And again, 0 is not a positive integer, so we can only see 4 as some c squared minus d squared. Now, can 4 be a result of some c squared minus d squared? After some trial and error, we will find that it is not possible because the nearest 5 is also 3 squared minus 2 squared. So 4 times 505 is also eliminated. So the only possibilities for us now are 5 times 404 and 20 times 101. Now, to actually find out, let me draw a line over here. No, not one line, but actually 2. Okay, so 1 line, and then we have another line over here because I want to make my thing more clearer. I'm not sure. Okay, so we have 5 times 404 and then 20 times 101 over here. So we can break these down further into 2 cases. So the first case here would be a squared plus b squared equals to 5. So for A, B, this set would either be 2, 1 or 1, 2, right? So we would have here, and then for C square minus D square equals to 101, no, 404. C would be equal to 102, and then D would be equal to 100. Because this, I have did this myself before, so I strongly encourage you guys to do this yourself first. So don't just look at my solution. I'm not sure, but if you want to look, it's also okay. Okay, so this is one of the solutions. And then for the second case, we would have A square plus B square equals to 404. This time, AB would be either 22 or the reverse to 20 because the order does not matter. And then we would have C square minus D square equals to 5. Well, C and D will become 3 and 2. Okay, now for the second case, so one of them is 20, one of them is 101. So for the third case over here, A square plus B square equals to 20. We would have AB as 2, 4 or 4, 2. Then C square minus D square equals to 101. C equals to 51. D equals to 50. Now, you might be asking, how did I get this? And again, I emphasize here, please try this yourself first before looking at my solution. I'm not sure, but maybe this is too late to say. Fourth case, A square plus B square equals to 101. Now, AB would be 10, 1 or 110. And then C square minus D square equals to 20. So C equals to 6, D equals to 4. Now, let's look at all the possible values of A, B, C, D, okay? So we would have 2, 1, 102, 100, 1, 2, 102, 100. And then this one, the next one is 22, 3, 2, 2, 23, 2. Then the fifth one would be 2, 4, 51, 50. 4, 2, 51, 50. This is a comma. Apologize. And then the last two would be 10, 1, 20, no, 6, 4. Then the last one will be 1, 10, 6, 4. So as you count, there are only 8 in total, as you can see here, 8. So the answer to question 16 as shown here would be 8, okay? So problem 16, answer 8, as shown here, okay? Now let's move on to problem 17. So this one's a bit tricky because I might take a longer time to explain, but now let's read the question. Given a positive integer n, the number 2n has 28 positive factors, while the number 3n has 30 positive factors. Find the number of positive divisors of 6n. So why do I say that this problem's a bit tricky? This is because some people might not know how do we count the number of positive factors of a number. Now, let me illustrate with a few examples. So, take for example the number, say, let me think, 210, right? 210. What we want to do with 210 is to decompose it into its most foundational form, meaning every number is composed of a certain power of prime numbers. So we see that 210 is equals to 2 to the power of 1 times 3 to the power of 1 times 5 to the power of 1 times 7 to the power of 1. Now, what we want to do if we want to count the number of factors is to add 1 to all of the powers. So 1 plus 1, 1 plus 1, 1 plus 1, and then another 1 plus 1. So we multiply these together, we get 16. Now, why is the plus 1 step necessary? Because 2 to the power of 0, which is 1, is also a factor. Then 3 to the power of 0, which is 1, is also a factor. So we're just multiplying this in terms of like 4. Now, to let you visualize it better, so we would have 2 to the power of 0 and then 2 to the power of 1 here. Then 3 to the power of 0, 3 to the power of 1 here, 5 to the power of 0, 5 to the power of 1 here, and then 7 to the power of 0, and then 7 to the power of 1 here. So you have 2 choices here, 2 choices here, 2 choices, 2 choices. So just multiply them together and then you will get 16. So one more example would be 72, which is 2 to the power of 3 times 3 to the power of 2. Now 3 plus 1 and then 2 plus 1. So we will have 4 times 3, which is 12. Now again, why the plus 1? Because we see here 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and then 3, 0, 3, 1, 3, 2. So just 4 choices, and 3 choices give us 12. Right. So this is a brief explanation. I hope that you guys using this will continue to solve the problem. Now we need to divide this whole thing into 4 cases, okay? And then I'll kind of briefly explain what these cases mean. Now I will use the tick and the cross to represent, okay? So cross means that this positive integer n is not divisible by 2 or by 3. So n is maybe say 5 to the power of something times 7 to the power of something. No one knows. And then for the second case, we'll consider the case where n is divisible by 2 but not divisible by 3. Then for the third case, vice versa, divisible by 3 but not divisible by 2. And then for the fourth case, n is divisible by both 2 and 3. Okay, so now let's look at the first case. So we have n equals to maybe say p1 some prime times n1, no, a1 times p2 times a2, blah blah blah, pn times an, okay? So side note, fun fact, so normally we will represent this by using this big pi, and then we will be multiplying this by pi ai. This just means this, if you know summation, this is just a summation but in multiplication form. Then the first one will be n equals to 1, and then n, yeah, something like this. Okay, this is not important. So the important thing is, so this does not involve 2 or 3, so none of these are 2 or 3. Okay, so 2n would be 2 to the power of 1 times all this, which is 2, and then plus this one, which has 28 factors. So n originally has x factors. Okay, so 1 plus 1 times x plus 1 equals 28. So x plus 1 equals to 14, x equals to 13, right? We are thinking that x would have 13 factors. But then we see 3n, which is 3 to the power of n times this whole thing, which is, again, 3 to the power of 1. So 1 plus 1 is 2. And then we see x plus 1 equals 30. So 2 times x plus 1 equals 30. And then we have x plus 1 equals to 15, x equals to 14. So if we see that x has 14 factors and x has 13 factors, so no. The number of factors for n is both 13 and 14. This cannot happen at the same time. So the first case, we no longer need to consider. Now for the second case, n is a power of n contains 2 but does not contain 3. Okay, so we have 3n equals to 2 to the power of pa0 times this whole thing. Wait, give me a moment, sorry. So we would have 3 to the power 3n equals to 3 to the power of 1 times 2 to the power of some a0 times this whole thing. So this would be 2 times, I don't know, a0 plus 1. Then this is another y plus 1 equals to 30. So we would have a0 plus 1 times y plus 1 to be 15. Now for 2n, we just have 2 to the a0 plus first power, no, 2 to the a0 plus 1 power, and then times this whole thing, which is 5, 7, or any other prime. So we would have a to the 0 plus 1, which is a0 plus 2 times y plus 1 equals to 28. Now when you divide both of these, this is first equation, second equation thing, we will get a0 plus 2, so sorry, a0 plus 2 divided by a0 plus 1 would be 28 over 15. Consecutive numbers having 28 over 15, which is not possible after you try yourself, okay? Not explaining it here, so the second case is also not to be considered. Now, for the third case, which is n is divisible by 3 but not divisible by 2. Okay, so n would be in the form of some 3 to the power of a0 times a bunch of other prime numbers. Okay, so 2n equals to 2 to the power of 1 times 3 to the power of a0 times this whole thing. So we have, no, I think this one should be a b0 to differentiate from the one just now. So this one will be 2 times b0 plus 1 plus another z, okay, equals, as we see above, 2n has 28 factors, so we have b0 plus 1 times z equals to 28 factors. But then 3n would have 3 to the power of b0 plus 1, times, sorry, I'm a bit nervous here, so plus this whole thing, so we will have b to the power, so we have b0 plus 2 times z equals to 30. So we would have something like, okay, give me a moment, let me check. Okay, b0 plus 1 times z would be 14 here because we divided by 2 already. So if we, again, this one, take this first equation, take the second equation, we divide, so 2 over 1, something like this. We would get b0 plus 2 and then b0 plus 1 because we have cancelled out the z's. We would have 30 over 14, then we divide this, 15 over 8, 7, which for consecutive numbers, again, is not possible, so this whole thing is to be deleted, okay? Now, for the fourth case, this one is a very long one, so we have to consider that this n equals to 2 to the power of c0 times 3 to the power of c1 times a bunch of other things. Now, as we can see here, I think I'll just stop at this question. Question 17 is a mouthful. 2n equals to 2 to the power of c0 plus 1 times 3 to the power of c1 times this whole thing, which will assume it to be, I guess, m, So we will have c0 plus 2 times c1 plus 1 times m plus 1 would be 28. And then 3n is 2 to the power of c0 times 3 to the power of c1 plus 1 because we multiply by 3 times this whole thing, which is an m plus 1. Then we will have c1 plus 2, c0 plus 2. Okay, c0 plus 1, sorry, is 30. Okay, so we, again, this one. So we divide the second term by the second equation by first equation. We can cancel out the m plus 1s. We would have c1 plus 2 and c1 plus 2, c0 plus 1. So sorry, this is really confusing even for me now. Okay, c1 plus 2 times c0 plus 1, and then we have c1 plus 1, c0 plus 2 equals to 30 over 28. Now this, okay, so doing this thing would be a bit harder, but I won't show how I did it. But the final thing I found was that this actually has a solution. So you should do this yourself. Pause the video for like 5 seconds or something. Ooh. Okay, so what I found here was c0 equals to, wait, let me think. c0 is equals to, c0 is equals to, I'm so sorry, give me a moment. Wait. Wait. This is, okay, 5, 6, 4, 7. Okay, so c0 is equals to 5, and then c1 is equals to, as we can see here, it's 3. So n is equals to 2 to the power of 5 times 3 to the power of 3. You guys can verify for yourselves. So sorry, this video is taking so long, I swear. Okay, so n is equals to 2 to the power of 5 times 3 to the power of 3 with no things at the back because it's already, if you add 1 to each of them, there will be like 28 or 30 factors already. So 6n, which is you just add the powers of 2 and 3 by 1, will be 2 to the power of 6 times 3 to the power of 4, right? Which will give us the number of factors for this one would be 6 plus 1, 7, then 4 plus 1, 5 is 35. So the answer to question 17 is 35, and then this is a very long windy one. I'm so sorry if you guys kind of just left, but I appreciate anyone who has stayed here. Okay, so since this took so long, we will be putting question 18 at the next section. I'm so sorry that I made those promises just now. Okay, so for this video, for the next video, we'll be discussing seniors question 18, 19, and 20. And I think this is it for this video. Like and share if you enjoyed it. I know it's not very enjoying, but anyways, like and share and subscribe. Okay, so we'll see you next video. Bye bye.